Okay, so to wrap up the third part here of section 7.2, probably a little bit easier than the first two parts. I'm going to pick up by just kind of recapping on the moments of inertia, right? So you should be familiar with the different moments of inertia for various shapes. However, in terms of actually being able to solve these, you should be able to derive several of these. So for instance, we've seen how to derive this, we've seen how to derive this one, we've seen how to derive this one. A thin hoop or cylinder is very, very easy to derive because the entire mass is all located that total radius away. So we should know where that comes from. Now, some of the shapes, like the sphere here, I don't expect you to have to derive the moment of inertia for a sphere. Right? So you don't have to know that one, but you should still be familiar with it and ready to roll with it, if you will. So make sure you are comfortable with those types of things. But again, the toughest part about this section, the biggest part, is making sure you get comfortable using some calculus, using the integrals to find these moments of inertia for different shapes. The good news, we actually have a theorem here, so the parallel axis theorem, which makes it easier to derive various moments of inertia if they are not those uniform, if they are not those standard, I should say, shapes. They still have to be uniform, but they don't have to be those standard pivot points. And so what the parallel axis theorem allows us to do is, what if the object is pivoted about some point other than its center of mass? So we've seen the example where the rod is pivoted over here and its center of mass is over here, but what if maybe the rod was pivoted about this point, right? If I asked you to find the moment of inertia for the rod there, we don't necessarily want to have to start over every time and do that whole integral all over again. Now we definitely could. We could do that. We could define this as maybe negative L over 4 and this is positive 3L over 4, and we could certainly go about it that way. But we don't have to do that. And so what the parallel axis theorem says here is, if I want to find the moment of inertia about a specific point, okay, so if I want to find the moment of inertia about a specific pivot point, then all I have to do is find the moment of inertia about the center of mass. So we know the moment of inertia for a rod about the center of mass is 1/12 ml squared. And then add that to the total mass of the rod times the distance away. So notice here d is the distance from the center of mass to the parallel axis. So in the example that I drew up above, if the center of mass is in the geometric center of that rod, and maybe this is a length of L over 4 away, then this would be another length of L over 4. So d in this case would be that distance between the pivot point, which is a distance of L over 4, right? So d would be L over 4 in this particular example. So then I would do 1/12 ml squared plus m times 1/4 L, that whole thing squared, and then I would just calculate this value. So the parallel axis theorem makes it way, way nicer, way, way easier to then calculate the moments of inertia for different pivot points as long as we know the moment of inertia about the center of mass. Okay, so anyway, we'll see a few examples of this. I think you guys will see that this does make life significantly easier. Hopefully you guys agree with me there as we see this. But anyway, use the parallel axis theorem to show the moment of inertia of a uniform rod of mass m and length L. Pivot about one end is 1/3 ml squared. Right, so we've already seen this using the integral, but we want to show it using the parallel axis theorem. So we want to show that a rod being pivoted about this end here would have that 1/3 ml squared. So again, we already know that's the right answer. We're just going to show it using the parallel axis theorem. So the parallel axis theorem says the moment of inertia about that pivot point equals the moment of inertia about the center of mass plus ml squared, or md squared I should say, not L squared. Right, so md squared. Well, the moment of inertia about the rod about the center of mass, I do need to know, and in all likelihood on an AP question they would probably have you derive that part first, and then maybe this would be part B as a follow-up to it. Okay, so the moment of inertia about the center of mass, we've already shown that it's 1/12 ml squared, so I won't make you show that again unless you guys just want to practice it again, right? In which case, feel free to pause and do so. But it is 1/12 ml squared, so we'll assume that we know that. So that's 1/12 ml squared plus the total mass, so it is the same m as the first one here, and then that's supposed to be a d, right? So d squared, now in this case d represents the distance from the pivot point to the center of mass. So the distance from my center of mass to the pivot point, which because I'm choosing one end would be L over 2, right? So I'm plugging in L over 2. The only thing I do have to be careful about is I'm plugging in that whole fraction and then squaring that whole fraction. So my moment of inertia equals 1/12 ml squared plus, this would be L squared over 4, so in other words 1/4 ml squared, which once we get a common denominator would be 3/12 ml squared. So I've got 1/12 ml squared plus 3/12 ml squared, which equals 4/12 ml squared, or better yet, 1/3 ml squared. So the moment of inertia makes it pretty easy to find out then that the moment of inertia of a rod pivoted about one end is 1/3 ml squared. I did not have to do another integral to get there. Now again, there's nothing wrong with doing it, but in this case it's a little bit easier, right? I think probably mathematically most of us could do this without too much difficulty as long as we know that moment of inertia about the center. Right? Anyway, hopefully that makes sense. Another example of this would be maybe they give you a uniform shape that we're not as familiar with. Okay, so maybe they give you a different uniform shape, so a rod with a certain density or what have you, and then they ask you to find the moment of inertia about that. The second they give you the moment of inertia about the center of mass, you're just using md squared, so that problem becomes very, very manageable. Okay, so make sure you're pretty comfortable with applying the parallel axis theorem. You will see this in several homework examples. We'll use it in one more time here in example 5, then look at a concept example to wrap up the section, and then we'll call it a day here with 7-2. So find the moment of inertia of a thin rod with mass m and length L that is pivoted about an axis 1/3 of the length from one end. So again, they're just choosing any random pivot point they want at this, right? So here's the center of mass. They're saying it's a length of 1/3, right? 1/3 the length of the rod from one end. Okay, so it's coming here. That's closer to probably 1/4. I'll try to make that better. There we go. About L over 3, right? So the distance here is about L over 3. So we're pivoting it around this point here. So I'm going to use my parallel axis theorem and hopefully show that this is once again pretty easy. All right, and feel free if you guys want to pause the video and try this on your own first and then just confirm with my answer here in a moment. But I'll assume you've paused it or are ready to just move on. The moment of inertia about that point there would be once again my 1/12 ml squared plus m times how far away from the pivot point is it, and that is the only thing you have to be careful about. If it's L over 3 from one end, it's actually only L over 6 from the center, right? We know the total distance there would be L over 2, so L over 2 minus L over 3 is actually L over 6. You get a common denominator and subtract them, right? So it's actually L over 6 squared, so I get 1 over 12 ml squared plus 1 over 36 ml squared. So once again, getting a common denominator, this would be 3 over 36 ml squared plus 1 over 36 ml squared. So then that becomes 4 over 36, or better yet, right, I'll just write it over here, 1/9 ml squared. So my moment of inertia about that pivot point would be 1/9 ml squared. And notice, obviously, if I'm choosing something other than the center of mass, what's actually happening to the coefficient in front? The coefficient, so like on the last example we saw, the coefficient was 1/3, which was much bigger, right? This example, which was still off-center, is 1/9, which is still bigger than 1/12. So notice the center of mass is always going to have the lowest moment of inertia. It's always going to have the lowest coefficient for the moment of inertia. If I start deviating more and more from the center of mass, then the moment of inertia is going to be higher. And that actually is a very important concept, something you should be comfortable with. Right? If they ask me where should I pivot this so that it has the lowest moment of inertia, I want to pivot it right in the middle. Okay, so no matter what the geometric shape is, whether it's a square, rectangle, circle, whatever it may be, if I want to pivot it so that it has the lowest moment of inertia, I want to pivot it in the geometric center so that it has the lowest moment of inertia. But anyway, one last example and then we'll wrap up this section. So quick conceptual example, and certainly one I want you guys to try, so feel free to pause and then just check with me in a moment when you agree or disagree. But the 4 T's we have below are made from 2 identical rods of equal mass and length, rank in order from the largest moment of inertia to the smallest moment of inertia. So again, this just comes down to a general rule of thumb and a general concept we should be comfortable with. Right? In order to make the moment of inertia higher, we need as much mass concentrated as far away as possible. In order to make the moment of inertia lower, we need more mass to be located closer to the pivot point, right? Closer to the axis of rotation. So when we look at these examples, we want to think about which one has the most mass located as far away as possible, and which one has the most mass located as centrally as possible. Right, so they want us to rank in order from largest to smallest moments of inertia. Well, if I look at these, which one has the largest moment of inertia? Well, A has the largest, right? A is going to have the largest because if I look at this as the axis of rotation, this entire rod is as far away from that as possible. And obviously this rod gets progressively further away as it goes down. So this definitely has the most mass concentrated as far away as possible. I'm actually going to jump to the other extreme because I think that's maybe easier to see sometimes. Which mass has, or which rod here, which T has most mass concentrated towards the middle? Well, C would have the lowest moment of inertia because this entire rod is pivoted directly around that pivot point, right, that axis of rotation. And then this rod only extends halfway either direction, which is the smallest amount that it can possibly extend, right, either direction. So C is definitely going to have the most mass concentrated on the axis of rotation, and therefore the lowest moment of inertia. So that's going to be the bottom end, A is going to be the high end, then we just have to figure out B and D. Well, B is going to have a lower moment of inertia than D because B at least does go through this right rod here. So it does have that one sticking up, which means there is some mass as far away as possible, but it does have this entire rod essentially negated there. So that means B is going to be the second smallest, which then means D, and if you look at D, it has a lot of mass concentrated further away, so D is going to be the second largest. So you should be comfortable again with these kind of ranking tasks. It is very, very important you get comfortable with moments of inertia, what properties make a moment of inertia go up, and what properties make a moment of inertia go down. Okay, so the two factors are obviously where is the mass concentrated and then how far is that mass away from the pivot point.